Please don't leave negative comments. It's just an example. I love all breeds of dogs. Let's assume that my family is looking for a new dog. Now, we're not. We have a perfectly serviceable Labrador Retriever named Princess, but let's just assume. Now, what I'm going to do is do something called a weighted decision, and this is kind of leading to a weighted decision matrix. And what we've got is the score, and it's really kind of, it's a total, so to speak, is the sum. Remember that symbol, the summation, right? The sum of the options score times the attribute weight. All right? And so what we've got is we're going to have a number of categories on which we're going to take each score or measurement for a particular option. So let's do an example. Let's see, we'll do a matrix. How about a Labrador? So a Labrador Retriever, and we're not really looking for a dog, so what I'm going to do is I'm just simply going to grab our neighbor's dog. Well, not physically. They have a Boston Terrier, all right? And then the people on the other side of us, they have a toy poodle, all right? So, what are the areas that we're going to critique these types of animals? How about shedding? All right. Another one. How about grooming? The grooming needs. Now, I grew up with Cairn Terriers, and to be honest with you, I wasn't always as proud as I could be to walk this dog. I mean, I wanted to have a manly dog. Now, that sounds a little, well, not quite correct. So let's just say that I want a dog that's confident. All right. The confidence measure of a dog. And the other thing is neither my wife or I like yappy dogs. So the yippiness. So there you go. Those are some of the categories. So we're going to rate each dog in each one of these categories on a scale from 1 being worst to 5 being best. All right. Now, Labrador Retrievers, they shed. And twice a year, they blow their coat. Every bit of fiber on their body seems to fall on your living room couch. So I'm going to put a 2 because they're not the worst, but they're pretty bad. Boston Terriers, they're not as bad. They're actually pretty decent. Poodles also are not too bad at shedding. They're not the best, but they are pretty good. The grooming, well, Labrador Retrievers don't require much. Neither do Boston Terriers, but toy poodles, as I understand it, are pretty much in need of regular grooming. Confidence level. Labrador Retrievers, pretty confident. Maybe not as confident as, say, a German Shepherd or something, but they're still pretty confident. Boston Terriers, a little less confident. Poodles, pretty nervous, right? Yippiness. My Labrador Retrievers, they don't yip. All right, but Boston Terriers, they're not great. And let me tell you, those poodles next door, they yip a lot. So I have a matrix now. Now, what am I going to do with this matrix? Remember, I've got this summation, which is going to allow me to multiply the option score by a given weight. And so this is the matrix of our option scores. I don't have the weights yet. Now, what am I going to do about the weights? What I'll probably end up doing is make a matrix that says, okay, for my wife, here are the importance, these 4 things. Here are the things that are important to her. And then for me, I'll make a weighting matrix for myself. What things are important for me? So we're going to have another matrix, which is rating David's weights and David's spouse's weights. And we got to do the same measures, so we'll do shedding, and these are going to be lined up as rows as opposed to the columns where they were in the dog matrix. So we got shedding, grooming, we've got confidence, and we have yippiness. All right? Now, for David, shedding's not really all that important. And what I'm going to do is, this will be kind of like percentages. What I'm going to do is take 1 and divide it as to, give more weight to the things that are more important to me. Well, confidence is pretty important to me, so I'm going to have that as a 0.5. Yippiness, I don't like dogs that make a lot of little high-pitched noises, so that's going to be a 0.3. The rest of them, grooming doesn't really matter that much to me, and shedding doesn't really matter that much to me. Now my wife, shedding is a little bit more important. Just getting hair all over the furniture and stuff, she's not all that crazy about. Yipping, she is sensitive to high noises, so she's going to put a high price or a high weight on yippiness. And that leaves about 0.2, which we're going to divide evenly across grooming and confidence. So what I've got are 2 matrices. Now let me show you what I do with these. Now first, let's copy down that dog matrix. So remember I had Labrador Retriever, Boston Terrier, and Toy Poodle. Now the Labrador Retriever scored 2, 4, 4, 4 whenever it came to, shedding, grooming, confidence, and yippiness, right? And then the Boston Terrier was 4, 4, 3, 2, and then the Toy Poodle was 4, 1, 2, 1. All right, so that is our matrix to define the type of dog. Let's take a look at the matrix, the weighted matrix. And so for me, for David, I had 0.1 for shedding, 0.1 for grooming, 0.5 for confidence, and 0.3 for the yippiness. And then my wife had 0.3, 0.1, 0.1, and 0.5. All right, now you'll see I already put a times there, because what I'm looking at is I am going to look at this expression right here and say I'm going to take 2 times the weight I gave shedding, 4 times the weight that I gave grooming, 4 times the weight that I gave confidence, 4 times the weight that I gave yippiness. And when I add all those together, the summation, that should come up with my personal score for the Labrador Retriever. Now it turns out that this is exactly the way you multiply matrices. If I've got a matrix, my matrix is on the left side, I'm going to take the row and I'm going to turn it and map it to the column of the matrix I'm multiplying it by. So we've got the 2 times the 0.1, the 4 times the 0.1, the 4 times the 0.5, and the 4 times the 0.3, and that will give me the Labrador score for me. And then the Boston Terrier score, I will take that and I will take the second row and I'll map it to the first column and then do that times 4 times 0.1, 4 times 0.1, 3 times 0.5, 2 times 0.3, and that will give me my score for the Boston Terrier. So what we're going to do is go ahead and perform this multiplication. And so I've got 4 columns that are going to map to the 4 columns from the first matrix that are going to map to the 4 rows of the second matrix. And so we've got 2 times 0.1 plus 4 times 0.1 plus 4 times 0.5 plus 4 times 0.3, and that is going to give us a 3.8 score. That's Dave's score for the Labrador. Same thing, 4 times 0.1, 4 times plus 4 times 0.1 plus 3 times 0.5 plus 2 times 0.3, and that's going to give me a 2.9 score for the Boston Terrier. And then for the Toy Poodle, 4 times 0.1, 1 times 0.1 plus 2 times 0.5 plus 1 times 0.3, and that is going to give me a score of 1.8 for the Poodle. So it turns out I like Labrador Retrievers. Now for my spouse's column, I've got for the Labrador Retriever 2 times 0.3 plus 4 times 0.1 plus 4 times 0.1 plus 4 times 0.5. That is going to give my spouse's score 3.4. All right. So she also kind of likes Labrador Retrievers, maybe not as much as I do. Boston Terrier, 4 times 0.3 plus 4 times 0.1 plus 3 times 0.1 plus 2 times 0.5. That's going to give the Boston Terrier a 2.9 score. And whenever you look at the Toy Poodle, 4 times 0.3 plus 1 times 0.1 plus 2 times 0.1 plus 1 times 0.5. When you add them all together, you get a 2.0. And what this has shown us is that for both my wife and I, we both seem to prefer the Labrador Retriever, at least based on this set of weights and this evaluation of each one of the dogs. But if for some reason they happen to run out of Labrador Retrievers and we need a dog, it looks like a Boston Terrier would be the next one on our list. So what does it take to multiply two matrices? Well, to multiply matrix A by matrix B, and what we're looking at is this A times B, right? Then notice that we had to match up the number of columns in matrix A with the number of rows in matrix B. In other words, we were taking a row of A and mapping it to B, so the number of elements in a row of A had to match the number of elements in a column of B. So, therefore, what you've got is if A is an M by N matrix, and we're multiplying it times B, which is an N by, we'll just say, K matrix, these values must be the same. All right. Now, what's the result? Well, the result is going to be C, which is going to be an M by K matrix. All right? And the example with the dogs, what we had was the dog matrix was a 3 by 4 matrix. The weight matrix was a 4 by 2 matrix, and what we ended up with was a 3 by 2 matrix. And so there were two columns, one column for me, one column for my wife, and then 3 rows, one row for each one of the dogs. So let's do another example. How about 1, 2, 2, 4, 5, 5. So there's my matrix A, and I'm going to multiply it by a matrix B, which is -5, 2, 4, 4, -2, -8. All right? And so I'm going to multiply these. And what I get is, for the first element, it's going to be the row of A mapped to the column of B. And so this is 1 times -5. So it's -5 plus 2 times 4, which is 8, which is equal to 3. All right. Next column here. What we've got is still on the top row, so we're still going to take A's row, but we're going to move to second column of B. So we've got 1 times 2 plus 2 times -2, which is -4, so this is equal to -2. Now, move to the next column, top row, 1 times 4 plus 2 times -8, so we've got 4 minus 16, which is going to give us -12. Now we move to the second row, so we go to the second row of A. So the second row of A mapped to the first column of B, 2 times -5, so that's -10, plus 4 times 4, which is 16, is going to give us a +6. Moving to the second row, second column, that's the second row of A, mapped to the second column of B. So 2 times 2 is 4, plus 4 times -2 is -8. So that's equal to -4. All right. Last column of the second row, 2 and 4 mapped to 4 and -8. So we have 2 times 4, which is 8, minus 4 times 8, which is 32, which is equal to -24. All right. Closing in on this, the bottom row. 5 times -5 is -25, plus 5 times 4, so that's -25 plus 20, which is equal to -5. Next one, we've got 5 times 2, that's 10, plus 5 times -2, which is -10, that's a 0. And then the last one, 5 times 4 is 20, plus 5 times -8, that's a -40. So we've got -20 for that last element. Give you an idea of how the multiplication is going to work out. Now, if we took exactly those same matrices, A, B, and we swapped them. So now what I'm going to do is I'm going to take B, which is going to be -5, 2, 4, and 4, -2, -8, and instead make it the A. And on the B side, we'll have the 1, 2, 2, 4, 5, 5. Now what we've got is, remember, this is a this is a 2 by 3, and this is a 3 by 2. And so the 3's match, and now what we're going to get as a result is a 2 by 2. So this 2 by 2 is going to be -5, this top left-hand corner, -5 times 1 plus 2 times 2 plus 4 times 5. That's going to give us 19. Top right-hand corner, -5 times 2 plus 2 times 4 plus 4 times 5. That's going to give us 18. Bottom left-hand corner, 4 times 1 plus -2 times 2 plus -5 times 5. Excuse me, -8 times 5. That's going to give us -40. And then this lower right-hand corner, 4 times 2 plus -2 times 4 plus -8 times 5. That's going to give us -40. And so you see we get a very different result if we swap the matrices, which means that matrix multiplication is not commutative. Remember, commutative said that it allowed us to swap the positions in a multiplication or addition. Works fine for basic arithmetic, but not for matrix multiplication. Now, one of the other rules that we do have, and I'm not going to prove them here, but we have a couple of other rules that the matrix multiplication does adhere to, things that you will recognize from your basic arithmetic. This includes the associative law. And so we have the associative law, and the way the associative law works is it says that A times B times C, and we're looking at matrix multiplication now, is equal to A times B, then times C. Matrix multiplication also adheres to the distributive law. The distributive law says that A times B plus C is equal to A times B plus A times C. Remember, you can't swap them, not commutative. In fact, something I didn't mention before is that just because A times B exists, and first of all, it doesn't equal B times A unless we have some really special cases, like for instance, if A equals B, then if A equals B, then swapping them will work because it's just the same matrix times the same matrix. But this A, just because A times B exists, does not mean that B times A existed. The previous example that was true, but with the dog example, not true, because when you swap them, the number of columns of A is not going to equal the number of columns of B. We talked about the additive identity, the zero matrix, before, but remember, in the very first lesson on matrices, we also talked about the identity matrix. And so if I've got this matrix, 1, 2, 3, 4, and I multiply it by the identity matrix, and if you remember, the identity matrix was 1s on the diagonal, 0s everywhere else. What's our result going to look like? Well, 1 times 1 plus 2 times 0, that's 1. This cell right here, 1 times 0 plus 2 times 1, that's equal to 2. The bottom row, first column, is going to give us this cell right here, this element. So 3 times 1 plus 4 times 0, that's 3. And then we also have this last element here, the lower right-hand corner. 3 times 0 plus 4 times 1 is 4. And you can see that the identity matrix times 1 matrix is equal to the original matrix. It's like multiplying by 1. But what if we swap these around? What if instead I had the identity matrix times something else? We know that multiplication is not commutative, but can the identity matrix be multiplied on either side of another matrix? So we have 1, 2, 3, 4 equals, and what we've got is 1 times 1 plus 0 times 3, that's 1. Then we have 1 times 2 plus 0 times 4, so that's 2. And then we have 0 times 1 plus 1 times 3, that's 3. And then we have 0 times 2 plus 1 times 4, that's 4. Looks like I can have the identity matrix on either side, works just fine. Now in our first lesson on matrices, we also talked about the transpose or transposition. All right, and the idea of transposition was that you took a matrix and you could flip it on its diagonal. Now, and we already know that if you take the transpose of the transpose, it will give you the original matrix. That is one that we've already talked about. But it turns out now that we have addition and multiplication added to our toolbox, let's see what the transpose does for us there. Turns out that the transpose, when you add two matrices together, that it is simply equal to the transpose of the first matrix plus the transpose of the second matrix. It looks like the transpose is distributed, we can distribute the transpose over addition. But can we over multiplication? Well, it's past or beyond what we were planning on covering in this lesson, but it turns out that the transpose can be distributed across multiplication if you also change the order of the matrices that are being multiplied. Before we go, let's do one more multiplication. I know I've been blowing through these really quick, but let's do one more multiplication. Let's do 2 times 2, 1, 5, 3. So I've got this 2 by 2 matrix, 2, 1, 5, 3 are its elements, and I'm going to multiply it by the matrix 3 minus 1 minus 5, 2. All right. Now let's go ahead and do this multiplication. What I've got are 2 times 3 plus 1 times 5. So that's 6 minus 5, that's 1. All right, now for the top right column. So we've got the top row of A times the second column of B. 2 times negative 1 plus 1 times 2, that's 0. So you've got negative 2 plus 2, that's 0. Now we'll do the bottom row of A with the first column of B. 5 times 3 is 15, plus 3 times negative 5, which is negative 15. 15 plus negative 15 is 0. And then we've got the bottom row of A with the last column of B. 5 times negative 1, it's negative 5, plus 3 times 2, which is 6, that's 1. And we got the identity matrix. What this gives us is that A times B is equal to the identity matrix. It's equal to 1. Now in math and regular multiplication, when you've got something that at times another thing is equal to 1, you know that the first element is the inverse of the second element. Well, in that case, we also do that. We say that for matrices too. What we've got is that B is equal to the inverse of A. So just like in algebra where we have inverses that can allow us to solve problems, we can use the inverse of a matrix in order to solve problems that are represented by matrices and their applications.